Hello students, welcome to the class mathematics. In the last class, we discussed the definition of an open sentence, connectives, statements, different types of statements and the negation of a statement. Now let us continue our class by defining some more important terms. First of all, let us see logically equivalent statements. Two compound statements are said to be logically equivalent statements if they have the same truth values for all logically possibilities. Which means when you are given two compound statements, if you can observe that those two compound statements have the same truth value for every particular case. For example, let us take two compound statements, that is negation of P or Q, negation P and negation Q. Now let us see the truth values of these two compound statements in a particular case, that is P is true and Q is true. In this case, negation of P or Q is false, and in the same case negation P is false and negation Q is false. So negation P and negation Q is also false. Here you see we have observed that these two compound statements have the same truth value in this particular case. Like that, we can also observe that these two compound statements have the same truth value in all the logical possibilities. So we can say that these two compound statements are logically equivalent statements. The next one is tautology. A compound statement which is always true is called a tautology. Now I am going to give a general example. I say that it is a pen or not a pen. Tell me children, what statement I have made is true or false? We can say that it is a true statement because I have said that it is a pen. Or what connective I have used? Disjunction. Or not a pen. In the case of disjunction, if any of the simple statements is true, that disjunction is also true. So it is a pen or not a pen is always true statement. So it is an example of a tautology. P or negation P is an example of tautology. And one more example we can see, P and negation Q implies P. It is also an example of a tautology. Now children, let us see how P or negation P is a tautology through the truth table. For that, first let us take the statement P. For the statement P, there are two possibilities. It is either true or false. Now let us take its negation, that is negation P. If P is true, negation P is false. If P is false, negation P is true. Now let us take the truth value of P or negation P. First case, if P is true, negation P is false, the disjunction is true. Second case, if P is false and negation P is true, the disjunction in this case also true. Now here you can see P or negation P is always true in all the possibilities. That's why it is taken as an example of tautology. And in the same way, let us see the truth table of P and negation Q implies P. For this, let us take some columns headed with P, Q, negation Q, P and negation Q. Finally, P and negation Q implies P. Now for the statements P and Q, there are four possibilities. They are true, 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 false, false, true, and false, false.
Now let us see the truth values of negation Q. If Q is true, in that case negation Q is false. If Q is false, negation Q is true. And in the same way, the next two truth values of negation Q are false and true. Now let us see the truth values of P and negation Q. This is the conjunction of P and negation Q. But we know that conjunction of two statements is true only when both are trues. That's why here once you observe first column and third column. Now here we can see in the second row only both are true, and in the remaining cases both are not true. That's why only in the second row P and negation Q will be true, remaining three cases will be false. Now finally the required statement, that is P and negation Q implies P. Here first statement is P and negation Q and the second statement is P. So from P and negation Q to P we have to observe. You see, what is the condition for conditional statement? First one is true, second one is false. In that case only result is false. So here let us search for true and false. In the first row we can see false true, second row true true, third row false false, and in the fourth row false and false. Here in any of the possibilities the statement P and negation Q implies P can't be true implies false. That's why result can't be false in any of the possibilities. So P and negation Q implies P is always true. Here we can clearly observe in this truth table. So children, here we can take P and negation Q implies P is an example of tautology.
In the same way, there is another type of compound statement which is contradiction. A compound statement which is always false is a contradiction. For example, you see, it is a pen and not a pen. Can you agree with this, with my statement? No, because it is always false. So P and negation P is an example of contradiction. Now let us define another term, quantifier. For this, I am taking one relation, that is x square is greater than or equal to 0. Now let us verify for how many values of x this relation is true. First let us take x is equal to minus 1, negative value let us take. So minus 1 whole square is greater than or equal to 0. That is 1 is greater than or equal to 0, which is true. For any negative value of x, this open sentence will become true. Now let us substitute 0 in the place of x. 0 square is greater than or equal to 0, which is true. And now let us substitute positive value. Let us take x is equal to 5. So 5 square is greater than or equal to 0. That is 25 is greater than or equal to 0, which is also true. So this open sentence will also become true for all the positive values of x. Now finally we can state that x square is greater than or equal to 0 for all x belongs to R, which is set of real numbers. So in this condition, the phrase for all explains to what extent the values of variable x are there. So the phrase for all quantifies the variable in this open sentence. Like this, the word or phrase which quantifies the variable in the given open sentence is called a quantifier. There are mainly two types of quantifiers. They are universal quantifier and existential quantifier. For the universal quantifier, we can take the phrases for all, for any, for every, for no. These are all examples of universal quantifiers. And in the same way, existential quantifier. For this quantifier, we can take for some there exists at least one. These can be taken as existential quantifier.
Universal quantifier is denoted by the symbol for all like this, and existential quantifier is denoted by the symbol there exists like this. Now let us see how to use these notations. When you write a trigonometrical identity, suppose sin square x plus cos square x is equal to 1, we mention that it is true for all x belongs to R. In the same way, when you write any quadratic equation, we write there exists an x belongs to R such that x square plus 5x plus 6 is equal to 0. Like this, children, we can use the notations of quantifiers.
Now let us see the negation of a universal statement. For that, let us take one universal statement, that is P. All the boys in the class are singers. Now here we have to write the negation of this statement. We know that the denial of the given statement is called its negation. First of all, let us see what the given statement is describing. Here, the given statement is describing that each and every boy in the class is a singer. Now, to deny this statement, if we can say that some boys in the class are not singers, then this can deny the given statement. So, for the statement, all the boys in the class are singers, negation will be some boys in the class are not the singers. So, in the same way, all the flowers are red. For this universal statement, negation is some flowers are not red. In the same way, let us write the negation of an existential statement also. For this, let us take one statement. Some numbers in the given set are prime numbers. Now, we have to write the statement which can deny this statement. If you observe the given statement, it describes that there exists at least one element in the set which is a prime. Now, if you can state that there is no number in the set which is a prime, then this statement can deny the given statement. So, for the given statement, some numbers in the given set are prime numbers, negation will be no number in the given set is a prime number. Now let us define the negation of all the four compound statements, that is disjunction, conjunction, implication and by implication. First let us see the negation of a disjunction, that is negation of P or Q. Now let us try to understand its negation through one example. Suppose I said I will give you a pen or pencil. This is my statement. Tell me, children, in which case you will remark my statement is false. Let us take the different cases. In the first case, I have given you a pen. So, my statement was true. Second case, I have given you a pencil. My statement is true. Third case, I have given you both a pen and a pencil. My statement is true. And one more case. This time, I have not given you a pencil and I have not given you a pen. It means I have not given you any of the objects. This time you will remark that my statement is false because I have not given you a pen, negation P, and I have not given you a pencil, negation Q. In this case, my statement will become false. So, from this example, we can conclude that negation of P or Q is equivalent to negation P and negation Q. Next one, the negation of a conjunction, that is negation of P and Q is equivalent to negation P or negation Q. Next one, the negation of a conditional, that is negation of P implies Q is equivalent to P and negation Q. Now let us try to understand this negation through one example. Let us take one conditional statement, that is if a parallelogram is cyclic, then it is a rectangle. A parallelogram is cyclic. If it is denoted by P, then it is a rectangle. It is a rectangle is denoted by Q. This statement will be if P then Q. Now this statement can be taken as a parallelogram is cyclic and so it is a rectangle. A parallelogram is cyclic P and so it is a rectangle. Now let us try to write its negation. A parallelogram is cyclic and so it is not a rectangle. That is P and negation Q. So from this we can state that negation of P implies Q is equivalent to P and negation Q. Next one, the negation of a biconditional, that is negation of P by implies Q is equivalent to P by implies negation Q or negation P by implies Q.
Students, let us know more about the conditional statement. In the conditional statement P implies Q, we say that P is sufficient condition for Q and Q is necessary condition for P. Now let us try to understand why P and Q are called sufficient and necessary conditions. For that, let us take one example. If x is equal to 3, then x square is equal to 9. Here we can see that x is equal to 3 is enough for us to conclude that x square is equal to 9. So x is equal to 3 is a sufficient condition for x square is equal to 9. Now let us see the necessary condition. If x is equal to 3, then it is necessarily from the condition that x square is equal to 9, because it is not possible for us to get from any other condition like x is equal to 1 or x is equal to 10. And also we can say that x square is equal to 9 is not enough for us to decide that x is equal to 3, because x can be minus 3 also. So x square is equal to 9 is not sufficient condition for x is equal to 3. So children, finally we can say that x square is equal to 9 is only necessary condition for the statement x is equal to 3. Students, now let us discuss the different forms of a conditional. For this, let us take one conditional, that is P implies Q. We know that in the conditional statement P implies Q, the statement P is called hypothesis and the statement Q is called conclusion. Now, if you interchange the hypothesis and conclusion, you will get the new form, which is Q implies P. This new statement Q implies P is called converse of the given conditional statement. Next one, in the given conditional statement, if you replace hypothesis and conclusion by their negations, that is negation P and a negation Q, you will get the form negation P implies negation Q. This form is called inverse of the given conditional statement. And the next one, that is contrapositive. For this, if you take the inverse of the converse or the converse of the inverse, you will get contrapositive. That is negation Q implies negation P. So, my dear students, these are the different forms of a conditional statement.